Alright, so today we're going to start by exploring exponential functions. And we're going to start by taking a look at the graph of y equals 2 to the exponent x. So in exponential functions, the exponent is x. When we've drawn this out, let's take a look at some of our key information. So let's start with the y-intercept. Take a look at your graphs. Where does the graph hit the y-axis? At 1. So the y-intercept is at 1. And remember that if we were doing that as a coordinate, we'd write it as 0, 1. The y value is 1. Now let's take a look at the x-intercept. Where does the graph hit the x-axis?
It doesn't.
Nowhere, right. So here there is no x-intercept. Now that's because there is a horizontal asymptote. So there's actually a horizontal asymptote that would run right along the x-axis. So we'd say the horizontal asymptote is at y equals 0. Again, your graph here is getting really, really close to the x-axis, but it's never going to touch it. Okay, so here are some functions that we have graphed. We graphed these functions with the red one is 2 to the power of x, the black one is 3 to the power of x, the purple one here is 10 to the power of x, then the blue is 99 to the power of x, and the green is 2000 to the power of x. So the bigger the base, the closer your line bends toward the y-axis. The reason is because when you have something that you're multiplying by itself, so for example, if I take the 10, okay, 10 to the power of x, what this really means is 10, when you're multiplying it by itself, x times. So what you're doing is you're multiplying by 10 over and over and over again. So think about if it was 2000. Okay, if it was 2000, that means you're multiplying by 2000 over and over and over again. So if you're multiplying repeatedly by 2000, your graph is going to get taller quicker. So that's why they seem to bend more toward the y-axis, because the taller they get quicker, they're going to, again, seem to be stretched upwards. Now let's look at these. How are these graphs all similar? How are they all the same? The y-intercept at 1. Yep. They all have the same y-intercept, and that is at 1. Good. How about their x-intercepts? No x-intercepts on any of them. Good, so there's no x-intercepts. And one more thing, what's the same about them? The horizontal asymptote for all of them is right there on that x-axis. So the horizontal asymptote is at y equals 0. Good. That's how they're all the same. Alright, so for the next step, we're going to draw some graphs that have a base that is between 0 and 1. So here we did 0.7, and you'll know that 0.7 to the power of x is way out this way. We have 1/6 x, which is here in blue. And then we have 1/4 x, which is here. So notice that these ones also bend at different rates, right? So what do you predict then? What about the ones closer to the y-axis now?
They're smaller, the decimal.
They're smaller, right? The smaller they are, the closer they are to y when they go this way. Good. What do we notice that was the same about these graphs?
They all pass.
The y-intercept. Good. Look, all of them have the exact same y-intercept at 1. Good. Okay, nope. Let's check that out in a minute though. So they all have the same y-intercept. What about their x-intercept? None. There's no x-intercept. You should be writing this down. There's a spot there about what's the same and what's different. How about their horizontal asymptote? It's all at y equals 0, right? It's all right there on the x-axis. And what is the only thing then that's different between these?
They're flipped.
They're flipped. Okay, so what we see, you guys, is the ones on this side are increasing. And remember, we always read a graph from left to right. So as I read from left to right, these graphs are going up. And then this side, we'd say, is decreasing, because these graphs are going down as they go from left to right. So that's what we say the difference is. They're either increasing or decreasing. And remember that for something to be increasing, we need a number bigger than 1 as your base. And for a number, or for a graph to be decreasing, we need a base that's smaller than 1, but still between 0 and 1. So it's going to be a fraction or a decimal. So again, we already said how these graphs are similar and different. They're different because they're increasing, decreasing, and they're similar in their x and y axis, or x and y intercepts, and their horizontal asymptotes. Now, if your base was negative, we tried the example here with a negative 5 to the power of x, and most of you got no graph. Again, that's because if you tried negative 5 to the power of 1, we'd get negative 5. But if we tried negative 5 to the power of 2, we'd get to positive 25. So your graph is actually going to flip-flop between positive and negatives as you try different numbers in there. Again, if you have a negative to the power of 3, it's going to be back in the negatives. So it would flip-flop back and forth.
So if it was any other thing.
So again, at a negative base, we'd say it does not exist. But if your base is 1, this would be like 1 to the power of x. Remember that you can multiply 1 by itself as many times as you want, and you'll always get 1. So if your base is 1, you're just going to get a linear function that hits a y value of 1. Alright, so here's what you really need to know. You really need to know that an exponential function is something in the form of y equals c to the power of x. We use c so that we don't get confused with our a, b, h, and k. Okay, so c means we have a base. Now, if the base is greater than 1, your function is going to be increasing. So that means, again, it's bigger than 1, even 1.1 or 1.2. You're going to get an increasing function. But if your base is between 0 and 1, notice how there's no equal to signs here. So it's only between 0 and 1, then your graph is going to be decreasing. Everything else is the same. They have the same y-intercepts, they have the same horizontal asymptotes, and they have no x-intercepts. Alright, so let's start by graphing this. We're going to graph this using a table of values. So using a table of values, remember we plug in different values for x. I always like to plug in negative 2, negative 1, 0, 1, and 2. And then once we plug those in, we'll get our y values. So the first one, if I put 4 to the power of negative 2, remember that a negative exponent flips your base into a fraction. So this is actually going to be 1 over 4 squared. Again, now notice the negative is gone. And 1 over 4 squared, when you square the top and the bottom, is 1 over 16. So the first part here would be negative 2, again, as your exponent. And then that would give us 1 over 6 as a y value. Same thing then with negative 1. So if I plug in the power of negative 1, that would give me 1/4 to the power of 1, which is 1/4. If I plug in 0, 4 to the power of 0, you guys, what's anything to the power of 0? 1. It's 1. That's why our y-intercept is at 1, because anything to the power of 0 is at 1. Then I put the power of 1, so 4 to the power of 1 is 4, and 4 to the power of 2 is 16. Then we can plot these on our graph. So once you've plotted your points, your graph should look something like this. Then we can find all of this information. So again, let's start with the x-intercept. What's the x-intercept of this? None. There is no x-intercept. The y-intercept is at 1. Right? We see it right in there at 1. We can also do the domain and range. So the domain of this function, let's think about our x's. Can I plug in any x?
No.
Yeah, I can. I can plug in any x value, and it's going to keep spreading out
Just gonna.
forever in the x's. So we say that x is an element of reals. The y's, though, have a restriction on them. All my y's are above 0. Do they ever hit 0?
No.
No. So we say that the y's are greater than 0. No equal to, just greater than 0. Now this graph, is it increasing or decreasing? It's increasing because it's going up as it goes from left to right. And the horizontal asymptote should be at y equals 0 because it would have an asymptote right along that x-axis. So let's move on here to example B. For example B, we're going to make a table of values again. Again, plugging in our x's is negative 2, negative 1, 0, 1, and 2. And then doing the exponent laws to find the y value. Then we'll plot the y values on the graph. So you should end up with a graph that looks something like this. And then you can find your x and y intercept, your horizontal asymptote, your domain and range, and notice that this function is decreasing. Pause the video here if you need a minute to write that down. Okay, and our final example here, example 2, you also have to be able to work backwards, where you're given the graph and you have to write the exponential function. So, we're going to put this in the form y equals c to the power of x. You guys, right away I notice that this function is decreasing. What does that tell you about your value of c? It's a fraction, yeah? It's going to be small, between 0 and 1. Okay, so I'm looking here, and I'm looking at my y values. My y values go from 16 to 4 to 1. So, if I'm making this a fraction, what fraction would take me from 16 to 4? 1/4, right? So we'd say that y equals 1/4 to the power of x. In other words, my y values are being divided by 4 each time. So I'm dividing 16 by 4 to get 4, dividing 4 by 4 to get 1. Could you predict what the next point would be? After 1? A quarter, right. So you keep dividing by 4. Good job, you guys. So we're going to take about 15 minutes then to work on these textbook questions.